Okay, let's next plot sigma x distribution for the model. To do that, highlight solution in the tree and select stress normal, and normal stress in the x direction is sigma x. So to remind ourselves of that, right click on the object and say rename, and I'll call this sigma underscore x. Enter, solve, and ANSYS will calculate sigma x. And let's remind ourselves quickly how that's calculated. So ANSYS takes the displacement field, differentiates it to get the strain field, and from that uses the Hooke's law to calculate the stress field, and sigma x is one of the components of the stresses. And while looking at the stresses, we can turn off the deformation. So I can go here and say, look at the undeformed model, and let me look at this as contour bands rather than smooth contours. And if I zoom in here, I see that there is not much variation in the z direction. So since this is almost in pure bending, the variation, and it's a plane stress situation, so a 3D analysis for this model is actually overkill unless you're using it as a stepping stone to do kind of a more complicated assembly analysis. If you want to make a copy of this image and save it to an appropriate folder, there are a couple of ways you can do that. The first way is to go here and select this option here and say image to file. The other way is to use the window snipping tool, and for those of you who are not familiar with the window snipping tool, I'll give you a brief demo. So you can come to the start button and type in snip, bring up the snipping tool, and just draw a rectangle over the area that you want to save, and then you can save it using this icon into an appropriate folder. I won't do that right now. And also, if you want, you can turn off the ruler by going here before you save the image. So you go to view, ruler. So you might not want to have the ruler in an image that you present in a report. And you can also save the animation. So after you play the animation at least once, you can go to this icon and say export video file. So you can export a video file and show it to mom to tell her that you're seriously studying and not seriously partying. Let's take a closer look at the sigma x variation on the front face. So I'll click on the z-axis to get the view along the front face, and I'll zoom in using the right mouse button. And so I can see that the sigma x goes from high tension to high compression in the middle of the crank. And if I click on max here, it shows me the location of the maximum. So that's where the tension is maximum. And if I click on minimum, that's the highest negative value. So that's where the compression is maximum. So sigma x goes from high tension on the lower fiber to high compression on the upper fiber, and it must go through a 0, which is where the neutral axis is. So I can click on probe, and if I probe the values around here, somewhere here it transitions from positive to negative, so the neutral axis is located somewhere over here. And I can increase the number of contours. So if I come here, click on the color bar, and I click here, I can increase the number of contours. So this view then is consistent with what one expects from classical beam theory. So let's take a view of the sigma x distribution inside the model using section plane. So I will go back to the isometric view, and I will re-enable the section plane that we created while interrogating the mesh. And let me highlight section plane and say I want to edit it and zoom in here. So I will translate the model to the right, and only then I can zoom in. And let's say I want to enable this side of the cut. So I make sure that I'm editing the section plane, and then if I click on that side of this dotted line, it'll enable that that side of the cut, and then I can drag the section plane. Okay, and I'll drag it to around where I have the max and the min and zoom in there. And that shows me and then let me just get out of the edit mode for the section plane. And I see that, okay, I see this nice linear variation between the tension and compression, and I don't see any I see hardly any variation in the z direction. So that view is completely consistent with classical beam theory, and in fact I can predict that distribution just by using hand calculations.